All right, let's take a look at exam 3 for the summer of 2019 for Organic Chemistry 1. Let's go through some of these problems here. And so we're just asked to basically predict and draw the major product or products for the following reactions. And, I give you guys a big hint, about stereochemistry here. So let's go through and do this. Now, I'm not going to show the mechanisms for all of these. I would strongly recommend you go through and do the mechanism for all of these. I just don't want to do that in this video because, time is short before the final exam. And otherwise, normally I would. But, hey, here we are anyway, okay? So HBr, just this one I will show, right? So we end up forming a cation, right? And remember, we have to always look next door to see a carbocation shift, right? So we know that our answer is going to have a shift with a bromine attached at one of the tertiary carbons, right? Either here or here. Either one of those is going to be equivalent, right? So either one of those are going to be equivalent. Now, we have to be careful because, remember, when we form a tertiary carbon, we have to worry about stereochemistry, right? So, right, that guy over there is not going to change. We can draw both of our products over here like this. And that guy's going to stay the same, right? And remember, when you're drawing R versus S, you just switch the wedge and the dash. Sorry for that noise in the background here. I'm making myself a cup of tea. So anyway, all right. So that's what we were looking for here, right? You have an acid. It's going to be used in the first step. We're doing an addition. We form a carbocation. We do a rearrangement. You look for the most stable cation, right? It's a planar compound. You make the R, you make the S. It attacks from both sides. Okay? Fantastic. So now we have sulfuric acid. We have high temperature. So sulfuric acid, high temperature with an alcohol, all three of these things. That's going to be our dehydration reaction. Right, our first step, we protonate the alcohol. We kick it off. We do an elimination. Right, so we do a Zaitsev elimination, right? Right, whoops. I didn't mean to do that yet. Right, we do an elimination to make the most substituted alkene. Right, what I mean by most substituted alkene as opposed to this, where we have a less substituted alkene. Okay? So for most eliminations, we're always going to be producing the most substituted alkene. Okay? So that's not the answer over here. All right, there it is. Bromine, we keep it cold and dark, right? You might see this also written as something like OCCl CHCl3 or something like that. That doesn't really matter. That's just a solvent. The point that I always like to emphasize is cold and dark here, just to draw a difference between the light and the heat one, which is a radical reaction, right? Doesn't really matter. Anyway, right, this is our halogenation, right? So there's all our carbons. Let's see if I can do this real quick here. Right, carbon, 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 right, carbon, 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 right? There's all of our carbons. Okay, so in this reaction, we're adding bromine across our double bond, right? So we're adding a bromine here. We add a bromine here, okay? This is anti-addition through the what we call the sumo mechanism, all this kind of stuff, right? All that's going on behind the scenes. And so remember, same thing. We have to pay attention to our stereochemistry. This guy up here is not a chiral center. We don't care about the wedge and dash there. Sorry, let me go back here real quick. Right, up at the top, we don't care about wedge and dash. Down here at the bottom, probably should care about it. There we go. Oops, sorry. Geez, I added too many carbons there. Sorry about that, guys. That's what happens when you try and make a quick video. All right, let me fill this back in here then, right? So carbon, carbon, carbon. Bum, 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 bum. All right. Now remember, this anti-addition, right? Anti-addition is extremely important to pay attention to, especially when you're on rings, right? You have to show that they're basically added trans to each other, all this kind of stuff, right? So here's going to be our answers for this, okay? All right, now we finally get into the meat of it for once. We have a tertiary leaving group. It's a okay, pretty good leaving group. We have a good nucleophile here, right? We have a good nucleophile, not a strong base really at all. So this is all lining up to be probably SN1 is probably going to be the preferred product in this case, right? So we have this here, right? That's probably going to be the product that we care about. Let's quickly run through this mechanism though, just to show you how I got there. Right, step 1, form carbocation. Step 2, in comes the nucleophile, right? Right. And then step 3, some base will come in and grab that off, right? It's going to be more of this guy over here, right? It's going to be more of the solvent in this case, right? Could you have done an elimination in this case? Yeah, you could have. Remember, sulfurs are really good nucleophiles, though, so more likely this is going to be an SN1. I didn't take off if you did an elimination. Just it's tough, right? SN1 and E1, it's hard to stop one from happening, right? We have clues about heat and all this other kind of stuff, but it's tough to really prevent one from happening. All right. Sorry, I didn't mean to scroll it there. Okay, looking around, we've got a secondary leaving group here. Right, we've got a polar aprotic solvent here. That's our excuse me, that's our buddy acetone. We got Ki, right? Excuse me, I got to mute the microphone here for just a second. Sorry about that. I had to cough really loud, so I didn't want to record all that. Anyway, Ki here. What we really see is I with a negative charge. Now, that means it is an extremely good nucleophile. Extremely good nucleophile, secondary leaving group. Not a great leaving group, but it is a secondary leaving group. Not bad, right? And so here we are going to end up adding an iodine, right? And remember, we invert the stereochemistry, right? At the carbon where the reaction's happening, right? This carbon right here, the red one, nothing's going on over there. Nothing's going to invert it, right? Nothing's going to change, okay? So I minus extremely one of the best nucleophiles. Also is a very good leaving group, and so there's some other stuff going on behind the scenes here. Acetone is what kind of helps us out, but that's not really relevant to what it is here, right? But you can look up a Finkelstein reaction is what it's called, okay? But there we go, SN2, good nucleophile, secondary leaving group, got it. All right, down here, find our leaving group, there it is, right? It's on a tertiary carbon, all right? So tertiary carbon, we're not going to be doing an SN2 reaction. We got an O with a minus charge, that's a powerful base, right? So tertiary leaving group, powerful base. This is all set up to be an elimination reaction, right? Let's show this mechanism real quick. This is E2, right? This is E2, boom, 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 right? We could pick any of the carbons out here, right? Any of those carbons are equivalent, I just picked the one that was closest to my base there, that's all. All right, so at the top, right, addition reaction, starting all the way back up here, right? Addition reaction to an alkene. Right below that, we're doing elimination with sulfuric acid, a dehydration reaction. Right, dehydration reaction. Addition of bromine, halogenation. Right here, SN1, right? SN2, E2 here, okay? All right. I think we'll finish up page 2 on this video, and then we'll go on to the next one. All right. So here I'm going to show you the mechanism for this top one here. All right. So we see an alkene. Right. We see an alkene with HBr. Okay. That should be addition, right? This HBr plus alkene. That should be firing the addition thoughts in your brain, okay? HBr. So we do the mechanism. We make a bond, we break a bond. Acids act like acids. And so we're given, you know what, let me go back and just change colors on my carbons there. Right? Okay. So as we've learned all semester long, right, you're always given two choices. If we're using an acid to protonate an alkene, you know we're going to leave behind a positive charge. So we can leave behind a positive charge there, or we're going to leave behind a positive charge here, okay? Those are our two choices. And so really we ask ourselves the same question we've always been, right? Where's the most stable carbocation that's formed? Well, both the red and the green carbon are secondary, okay, so that's not really a selection criteria. But over here, right, we can do a resonance structure, okay, stabilizing that positive charge. And what do we know about stabilizing positive charges? If it can, it will, right? That's the name of the game, stabilizing your positive charges. Here, nothing to stabilize it, right? Secondary carbocations, not great, right? They can form, but, you know, not the best. And you can say, well, what if I form the carbocation here and then it does a hydride shift? And, well, then you end up back at this position. You know, you end up at the same place anyway, so what difference does it make, right? You're doing an extra step that you don't need to. As I mentioned in class, if I ask you guys to run 3 miles or 2 miles, which one are you going to pick? So here's the best, most stable carbocation. We just finished this up by bringing in our nucleophile then. Yep. All right, boom, boom, ClBr. Okay. So that's what most of our product's going to look like. Oops, I meant to do that wedge and dash. So wedge, dash, ClBr, wedge, dash, BrCl. Okay, either one of those. Well, not I shouldn't say either one of those. Both of those are going to get formed. Okay, just trying to capture everything on the screen here. Fantastic. These next two questions have the same mechanism as for the very first problem, right? The very first problem that I looked for. This one gets a little bit tricky, right? There's a couple different answers for this, so you just got to be careful. All right, you're might end up with this or this, right? Or, right, this, or this, right? Now, which one of these is probably going to get formed the most? Well, likely these are the products that we're going to make the most, but can we dismiss these right here? The answer is not really, right? So depending on, depending on what we're looking at, we have to be careful about what products get formed, right? So, all right. Now, again, we're left at the same point here, right? What's our product here? Well, here, okay. These blue carbons are all identical, right? They're both secondary. There's not going to be any shifts. Those are the products that we're going to make, right? Mercury acetate, so we have our oxymercuration, demercuration, right? So again, we got a series of reactions here, right? Oxymercuration, demercuration. That means we add an alcohol across a double bond. The alcohol gets added Markovnikov to the most substituted side, right? And we don't have a, right? So we get a couple different products that get formed along the way, okay? No carbocation formation, right? No carbocation formation in this, so we don't have any rearrangements, no shifts, and that's the useful part of an oxymercuration, right? In the previous, right, in the previous three examples here, right? HBr, HCl, HCl, right? Whenever you see an acid used, right? Whenever you see an acid used, that typically means we're going to form a carbocation along the way, right? When we form carbocations, that means we're going to have to worry about rearrangements and shifts and all that other kind of stuff, right? But with oxymercuration, we do a hydration reaction, right? We're adding H and OH, but we don't have any rearrangements, right? Because we don't form a full carbocation. We do our little sumo thing, and that's about it. All right. Last problem. Okay. There you go. Now, for argument's sake, right, we have a syn addition of the H2. Right, the H's are added on the same side, so just pay attention to that. Okay, but it's just fine to draw that, right? We're just doing a hydrogenation. We don't really, it's not going to make a difference where those hydrogens get added, right? Alrighty, so addition reaction, addition reaction, addition reaction, addition reaction, addition reaction, right? All addition reactions here. Okay, that's the end. We'll end part 1 of the video here, and hopefully I can get the next one up for you guys pretty soon.